Hello and welcome to Toddcast number 61. We're transitioning from alcohols, which we spent the last seven Toddcasts on, into ketones and aldehydes, which we actually have been doing, being that the product of alcohol oxidation is often a ketone or an aldehyde. So it's really hard to separate these two topics, but I have, and hopefully they'll tie together nicely. So this is kind of an alcohol review inadvertently. But go ahead and get started. Recognizing the functional groups is key. Carbonyl, there's so many different types of carbonyl compounds that will, as we slowly learn them, it might get overwhelming. The simplest ones are the aldehyde, where there's an H on the carbonyl. This one has two H's, so it's still an aldehyde. It's one carbon, so it's methanal, the IUPAC name, but it's commonly known as formaldehyde. You also have propanone, which is a ketone because it has no H's on here. It's two R groups. So just note of interest, the first one is an aldehyde. And I could have circled either hydrogen. And the second one is a ketone because there is no H on the carbonyl. A little more complex molecule, vanillin. It's an aldehyde because it has a carbonyl. Whatever group we have here, that's fine, but it has an H. And then a ketone, carbone. You have a ketone with two R groups. So a carbonyl with two R groups is a ketone, fairly common. So these are functional groups you'll see repeatedly in OChem, in biocompounds, very, very essential, I guess, functional group, acetyl bond O, to all sorts of chemistry. Okay, so want to look at some biological versions of it, as mentioned, very common in bio. One of the more interesting ones, I think, is a terpene known as trans-retinal. Terpenes come in multiples of 5 carbons. They're built from a 5 carbon species called isoprene. So if you had 5 plus 5 plus 5 plus 5, for instance, as is the case here, you end up with 20. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So I'm added 2, so 18, 19, 20. So you have 20 of them all together. You also can fragment it into 4 carbon pieces with methyl on the side. So 1, 2, 3, 4. That's a fragment. So this is a new bond that's formed. 1, 2, 3, 4. New bond that's formed. And so it's a building block biologically. But transretinal, it's basically the molecule that you find in rhodopsin. So it interacts with this pi bond here, interacts with light of the right frequency around 509 nanometers. And when it does, your rods, this bond will break, it'll rotate, it'll open up a pathway so that calcium can bind, and your rod will send a signal on the optic nerve to say light has stimulated this point. And so transretinal is responsible for seeing light and dark. Okay, so basically brightness. There are also various sex hormones, plenty of them. You will learn that in your bio classes when you take histology. But estrone is one of the sex hormones. It's one in the estrogen group. There is also 4-hydroxy trans 2-nonanol, and it's basically when you oxidize a fat up, you get a signal molecule. So this is, I guess, just one example of a lot of times what we end up doing. If we take some sort of alkyl group, such as terpene, for instance, or a steroid, and you functionalize it differently, and you get some messenger molecule, whether it be a hormone or whether it's just a messenger molecule to be made on demand. Prostaglandins fall in similar category, but just compounds that, by changing functionality, changes the message it sends to another molecule, another receptor site. And then finally, testosterone, another sex hormone. Typically, estrone is thought of as the female sex hormones, or estrogen is a collection of them. Estrone is one of them. And testosterone, typically thought of as a male sex hormone. But for those who've taken bio, you're fully aware that they're not exclusively one gender or the other. Okay, onward we march. So aldehyde forming reactions revisited. So we oxidized alcohols to turn them into aldehyde, but one of the constraints was we had to make sure we put a poison in there. So just revisiting this, this is a primary alcohol. Primary alcohols have 1, 2 H's to lose. You only want it to lose 1 H, so you have to put pyridine in there. That compound is the P. Pyridine must be present. And it actually stands for pyridinium chlorochromate because when you add HCl, you actually protonate this from pyridine to pyridinium. But the point being, the presence of pyridine, which couples with the absence of water, prevents this from going into this form it has to go into for further oxidation, so it stops at the aldehyde. Okay. Ozonolysis of an alkene when there are H's attached. So for instance, in this case, we have an H right here. So that H is going to be right here when we form our product. So if you remember, ozonolysis cleaves this and then adds an O to the sulfur. So the sulfur or dimethyl sulfide becomes dimethyl sulfoxide. And then two sides here become a carbonyl. Ketone gets two R groups. This one becomes an aldehyde because there's an H right there. And then one more reaction, hydration of a terminal alkyne. So if we use BH3 equivalents, so BH3 is gets more and more selective if I add it in, let's say, a 1 BH3 to 3 alkene ratio. It gets more selective with each additional R group it adds on for anti-Markovnikov. So we stack the deck when we use 9-BBN. It's a boron that already has two R groups on it and only one H. And because the 9-BBN, the ring system is so bulky, the H goes on to the less crowded carbon. Or I'm sorry, the B originally. My mistake. I apologize. The H and then the B with the bulky group. And I'm not going to do a good job drawing, but this bulky ring system forces it to go H there, boron there. In doing so, it gets rid of that bond and one of the bonds in the triple bond. So you end up with a double bond where the H is on the more substituted and OH goes on less substituted. This is known as an enol. And enols undergo something called tautomerization to turn into a ketone. Okay, so hopefully this reaction sounds somewhat familiar. So keep in mind, I had a triple bond there before I added the group in there. So these are three common reactions you've already done. Want to revisit ones that form ketones. And it ends up, we just saw that the ozonolysis ends up forming a ketone as well as an aldehyde. So that one you already know. But oxidation of a secondary alcohol. So secondary alcohol has one H to lose. If you oxidize it, turn it into a carbonyl, you'll get a ketone. This is known as Swern oxidation. Again, I don't care if you memorize the names, but I need to say them enough times so that you, if you hear it, you can hang out with chemists and name drop. We do like to do that in chemistry for whatever reason. But you have paracarbonyls with Cls on them, connected by a carbon-carbon bond. Once you get rid of the chlorines and pick up O's, so once you get, in doing that, it wants to get reduced and oxidize that up. Okay. And ozonolysis is mentioned, exact same ozonolysis reaction we just did. So keeping in mind that aldehyde was one of them, but a ketone was the other one because we have R groups right here. So those are R groups. So you get a ketone. And then hydration of alkyne, but not using the boron method. So don't use an IBVN. Instead, use something that gives you Markovnikov. H goes where H is. So if we get that, we'll put the H here. We'll put the R group there. Actually, I apologize, the OH group there. Get rid of one of the pi bonds. And again, tautomerization. So we're going to go from the enol to the ketone. So it looks very familiar. And in the previous one, when I said ketone, I just realized I should have said aldehyde. Okay, so we reviewed reactions you've seen before, given nomenclature you've seen before. Not much of this podcast, but hopefully it's that step into the fundamentals of the material. And we'll get more into the reactions in future podcasts. So thank you for playing along, and I will see you at the next podcast. Thank you. Bye.